This 280 VHD has obviously suffered a catastrophic failure. On close inspection, it can be seen that the gear teeth of second gear countershaft and second gear main shaft have been sheared and torn loose. More than likely, this occurred due to driver error or abuse. The rear wheels of the vehicle may have been spinning on ice or loose gravel and then suddenly hit dry pavement. The shock sheared the teeth from the gear, and a loose tooth became wedged between the idler gear and the countershaft gear, causing tremendous damage. This is an aluminum synchronizer and its cup. This synchronizer has failed due to a lack of lubrication, but low oil level probably didn't cause this failure. The most probable cause was improper towing. As in most manual transmissions, the countershaft must be turning to lubricate the gears, synchronizers, and bearings on the main shaft. If the vehicle is towed improperly, only the main shaft turns, building a tremendous amount of heat, which can result in a synchronizer failure. Further towing would result in additional destruction of the synchronizers, and eventually the entire synchronizer cones would be destroyed, and nothing but the hub would be left on the main shaft. If the towing continued, more damage may be incurred, such as bearing failure and gears seizing to the shaft. Proper towing requires that either the rear wheels of the vehicle be raised off the ground, the axle shafts be removed, or the drive shaft be removed from the vehicle. This is a synchronizer cup which has been used beyond its normal service life. It is recommended that any time a transmission is serviced or rebuilt, these cups be inspected and replaced if any surface distress is found, such as that shown here. The cups should only be reused if they have a perfect mirror finish across their entire face. A synchronizer cup cannot successfully be repaired by using emery paper or crocus cloth to clean up the surface. This synchronizer ring has failed in the area of the split pins. They have worked their way out of the edge of the synchronizer and eventually sheared the blocker pins. This type of failure is caused by a severe torsional vibration generated in front or most commonly behind the transmission. Some common causes of transmission vibration are unequal universal joint working angles, driveline out of phase, rough running engine, or worn or loose engine mounts. This is a close-up of a synchronizer ring. The oil release grooves that are machined into the base of the synchronizer on a horizontal plane are worn. The synchronizer should not be reused in this condition because it would tend to hydroplane on its mating cup, causing a loss of friction, which results in clash in the transmission. The uneven wear shown here could also indicate excessive synchronizer end play. This synchronizer ring has the proper grooving, but you can see fine flakes of metal pressed into the bronze material. This metal has chipped off the gear teeth and become embedded in the soft bronze material. These chips of metal will render the synchronizer ineffective. The aluminum synchronizer is somewhat harder and is not as apt to allow these metal particles to become embedded in it. This is a main drive gear which has had its teeth chipped off due to misalignment between the transmission and the engine. Because of the misalignment, the main drive gear no longer has full contact with the countershaft drive gear, and all loading is then carried on the leading edge of the gear teeth. This concentrated load exceeds the design strength of the material. This main drive gear tapered roller bearing has failed due to misalignment of the gear, which placed an excessive load on the end of the bearing. Once a bearing starts to spall, rapid failure occurs. This is a main drive gear ball bearing. You can see the wear and spalling patterns start at the edge of the bearing and run down through the center and taper back off towards the edge again. This is another example of misalignment. This failure was caught in the early stages, but if allowed to go on too far, the bearing will fail totally. The damage will destroy any evidence of misalignment, and the diagnosis would probably be confused with a contamination problem. Another failure caused by engine transmission misalignment is wear of the clutching teeth in the direct drive position. The clutching teeth of the hub and drive gear are not designed to operate with any relative motion. The motion created by misalignment will result in the wear shown here. Still another example of misalignment is the pilot bearing wear on the inside of the main drive gear. The main drive gear is no longer running concentric with the main shaft, causing edge loading of the bearing. These are some bearing rollers out of the main drive gear from where the main shaft would normally run. As you can see, they have worn on an extreme taper, indicating that the main drive and main shaft were not in alignment with one another, creating a heavy load on one end of the bearing. In this slide, the seal track, or the area where the lip seal runs on the main drive, has been polished very wide. This polished area should only be as wide as the seal lip. When the wear pattern gets this wide, you know that the main drive gear has been misaligned, or the seal has been improperly installed. The main drive gear pilots into the bearing in the engine's crankshaft. If this bearing fails and ceases to turn, the main drive will spin inside the bearing race and wear out. It is recommended that any time the transmission is removed from the vehicle, the bearing should be inspected and, if necessary, replaced. This ball bearing has failed due to contamination. Bearings are more susceptible to debris in the oil than any other component in the unit. The bearing on the left is a new bearing. The bearing on the right is the one that has failed due to a lack of lubrication. This tapered bearing failed due to heat generation caused by water getting into the oil. Lubricants contaminated with water can no longer maintain an oil film sufficient to prevent metal-to-metal contact. Gears have seized on the main shaft in this case, and the shaft snapped at the radius between the third and fourth gear. This failure is probably the result of a lack of lubrication or a torsional vibration which caused the gears to wobble and gall the shaft. The gear on the right is a new gear. The gear on the left has failed due to improper clutch adjustment or driver error. To prevent this, the driver should allow sufficient time for the gearing to come to a complete stop after disengaging the clutch before shifting into first or reverse. This gear has developed a frosting pattern on the face of the teeth. A gear should not be replaced because of frosting unless other signs of distress are noted. This gear is frosted but also has developed pitting concentrated at the root of the tooth. Gears in this stage of pitting should be replaced. This gear shows destructive pitting and should be replaced, or noise and fatigue fractures may occur. This gear has failed due to contamination. The gear face is scored and the top of the gear is rounded off. A gear in this condition should not be reused. This is an example of an impact fracture which was caused by a severe shock load or a foreign object passing through the gear mesh. The shiny spots on the fractured area were caused by the mating gear after the initial failure. In addition to the gear which has suffered a tooth fracture, the mating gear should also be replaced. All gearing should be inspected for possible damage caused by the broken tooth running through the transmission. This gear has failed due to a fatigue fracture. This type of failure can be identified by the beach marks, which are made as the tooth progressively cracks under a load. The tooth has been shocked many times throughout its life and has finally broken off. Usually in this situation, other teeth on the gear will also be cracked or broken. This failure is probably the result of driver error or an overload condition. This idler gear has a wear pattern across half the face of the gear teeth, and one tooth has broken off only on the worn side. This failure is caused by improper shimming or excessive loading of the power takeoff. The gear shift lever has an advantage of 7 to 1 against the fork. If too much pressure is applied by the driver, the fork can bend or break as shown here. This front countershaft bearing was pressed too deeply into the case, allowing contact with the countershaft. The continuous loading eventually cracked the bearing, causing an oil leak. Using the information presented in this program, along with your mechanical skills, will help you determine the cause of the failure and when component replacement is necessary.